Hello, my name is Professor Ajban, and this is the second episode in the Quadratic Series. Again, we're going to be looking at something that we need to learn how to do before we can look at things like factoring quadratics, or solving quadratics, or even graphing quadratics. We're going to be looking at how to multiply polynomials, specifically using the foiling method. I'm going to teach you three different ways how to multiply polynomials, and this is the first of those three ways. We're going to look at three examples in this video. The examples that we're going to be looking at are on the screen now. So if the problems that you're trying to do look like this, you're in the right video. If you're looking at these and you think that you know how to do them already, I would recommend going to episode 3 of the Quadratic Series. But for everybody else, let's jump into it. So before we even take a look at foiling and what that means, I want to make sure that everybody understands the distributive property. So the distributive property, to recall some information, is going to be when we have a term in front of a parentheses, and in this case we have a trinomial in the parentheses. So the distributive property says that we want to take this term that's in front and distribute it, meaning we need to multiply it, to each term of the polynomial in the parentheses. And it's very common to use a line to designate that you're multiplying that term with the corresponding term. So we need to multiply 2x and 7x squared. So we multiply the coefficients. 2 times 7 is 14. And then we have to multiply the variables. So this x has an exponent of 1. And if we're multiplying variables with the same base, we add the exponents. So x times x squared gives us x cubed. I need to do 2x times negative 3x. So 2 times negative 3 gives me negative 6. X to the first times another x to the first is going to give me x squared. And then we have just the coefficient, so we're just going to multiply the 6 and the 2 and get 12x. Okay, so this is a recall for the distributive property. And we're going to take this idea and apply it to multiplying polynomials to see where the foiling comes in and what the foiling actually means. Alright, so starting off with our first example where we are multiplying two binomials. I have the binomial x plus 3 times the binomial 2x minus 5. Now this looks kind of similar to this, but instead of having one term being distributed in, I have a binomial being distributed into another binomial. So I'm still going to do it the same way. I'm going to take this term in front and I'm going to look at x plus 3 as the entire term that's in front and distribute this entire thing to the 2x and then the entire thing to the negative 5. So if we do that and we distribute it, we can take this 2x, I'll try and color code, we can take this 2x and we are multiplying it by this binomial x plus 3. And I can take this negative 5 and we are multiplying it by the binomial x plus 3. Now I have two different pieces that look very similar, in fact nearly identical, to the process that we looked at in this recall example. So this should be pretty straightforward. I can take this 2x and distribute it into the x and the 3, and take this negative 5 and distribute it into the x and the 3. So 2x times x, 2x squared. 2x times 3, 6x. Negative 5 times x, negative 5x. Negative 5 times positive 3, negative 15. Now we're not done just yet. We need to simplify our answer. And the way we simplify answers when we're multiplying polynomials is by combining like terms. So I'm going to look through this entire problem and look for things that are similar, specifically the degree of each of the terms. So I have a single 2x squared. I don't have any other x squareds. I have a positive 6x and a negative 5x. If I combine those because they are like terms, we end up with, well, 6 minus 5 is 1, so I have a positive 1x. And then we have a single constant term, minus 15. So this down here would be our final answer. It has been simplified. We combined like terms. All right, let's go to the next example. We have two binomials being multiplied again. Now, I don't think many of you are going to want to work on distributing a binomial and then distributing each constant term into the binomial. Instead, we have this handy acronym, FOIL. So FOIL stands for first, meaning we take the first term of each of these binomials and we're going to multiply them. Outside, meaning we take the outside two terms and multiply them. Inside, meaning we take the inside two terms and we multiply them. And then last, meaning we take the last two terms and we multiply them. All right, so it's a handy acronym that makes sure that we multiply each term with each possible other term in the other binomial. Okay, so let's look at this. What do we get? The 3x squared times 2x is going to give us 6x cubed. The 3x squared times negative 5 is going to give us negative 15x squared. And the negative 1 times 2x is going to give us negative 2x. And then finally, the negative 1 times the negative 5 is going to give us positive 5. Now we would look for any similar terms in this so that we could combine like terms and simplify our final answer. And if we look through it, we see that we have a single x cubed term, a single x squared term, a single x term, and a single constant term. So everything is already simplified. There's no like terms to combine. All right, so if you're multiplying two binomials, there's no need to go through and do it this way, although this is perfectly adequate. Instead, you can use the FOIL acronym and you see you kind of get to the answer in one step rather than the two or three that it would take to do it this way. But this way is where this foiling idea comes from. But what if you don't have two binomials? What if you have a binomial and a trinomial? Well, in that case, the FOIL acronym, it doesn't work. FOIL only works, the acronym at least, if you have two binomials. But we can apply the same idea in that we want to take the first term from the first polynomial that we have, in this case negative 2x, and I want to distribute it to each other term in the other polynomial. And then I want to take the next term in my first polynomial that's being multiplied, in this case 7, and distribute it to each of the terms in the other polynomial. So we're going to take 7 and multiply it by 3x squared, the 5x, and the negative 1. If we do this, negative 2x times 3x squared gives us a negative 6x to the fourth. Negative 2x times positive 5x gives us negative 10x squared. Negative 2x times negative 1 gives us a positive 2x. And then we can work on the other ones with the second term. So 7 times 3x squared gives us 21x squared. 7 times 5x gives us 35x. And 7 times negative 1 gives us negative 7. We see we end up with 6 terms, and I drew 6 lines. Okay, so the lines are like a visual way for you to see what needs to be multiplied, and you can count the number of lines to know how many terms you should end up with. And don't forget, we're not done. We need to do one more thing. We need to combine like terms. So if I look through this, I'm looking through it, I see I have negative 6x to the fourth, I have x squared x, x squared x. I don't have any other x to the fourths. So I can go ahead and write that one down, negative 6x to the fourth. I don't have any x cubes. That would be what I would normally write next. So we can go to x squareds. I have negative 10x squared here, positive 21x squared here. If we combine these, meaning we add the two coefficients together, negative 10 plus 21, we get positive 11x squared. The next highest degree that I have is a single x, meaning the exponent is 1. I have 2 of them here, and I have 35 of them there. If I combine them, well, 2 plus 35 is 37x. And then I have a single constant term, a negative 7. Okay, so the idea of foiling comes from the repeated distributive property. And this idea of foiling, this handy acronym, is also derived from this repeated distributive property. But this foiling acronym only works for multiplying two binomials, but we can extrapolate the same concept, the same idea, the same strategy to multiplying any amount of polynomials. So, drawing more lines when we have large polynomials, it gets a little messy. If I had a trinomial times a trinomial, I would have 9 lines. If I had a polynomial with 4 terms times a polynomial with 3 terms, the number of lines will just keep growing and growing and growing. So there is a method that keeps everything nice and organized, but it's still very visual. That's called the box method, and that's what the next episode is going to be about. If you found this video helpful, consider giving it a like and consider subscribing for more math lessons. If you have a question, comment it below and I'll do my best to answer. Alright, and we'll see you in the next one.